Good morning. My name is Evangelos Karampotsis and I am a PhD candidate of the University of the Aegean. I am here to present you preliminary results from the application of intelligent techniques to estimate the performance of unreliable two-machine production lines with random processing times. Serial production lines, SPL, are an essential part of production systems. Those have been thoroughly studied as the global economy relies heavily on them for the well-being of the world's population. A rather tricky problem of SPL is the estimation of throughput, EOT. The throughput expresses the final products per time, produced by a production line when this line has machines subjected to failure. Three parameters increase the complexity of EOT: the mean service rate, the mean failure rate, and the mean repair rate of a machine. It is noteworthy that there are no known closed-form formulas for EOT for big production lines, such as those of car manufacturers, as there are for small serial reliable production lines. In our work, we approach the specific estimation problem for an unreliable two-machine production line with computational intelligence methods. More specifically, a well-known model, which uses the queuing networks and Markovian analysis, applied to construct suitable fitness cases for a small production line of two workstations subjected to failures. These fitness cases used to train artificial neural networks, ANN, and genetic programming algorithms, GPA, to assess the ability of these methods to address the problem of EOT. Finally, a new set of unseen data, which was constructed using the same method as the previous ones, was used to validate these two AI methods. The specific figure shows the production line under consideration, where each machine MI when operates is in state 1 and at a rate lambda, shuts down in state 0 due to a fault and stops. Its restoration begins immediately, and it is repaired at a rate of mi. So it starts producing again. Each machine's mean service rate during its operational phase is ρ(i). The above-mentioned mean rates are the known parameters of exponentially distributed processing time. Also, the time between failures and the time to repair are exponentially distributed. The states of the system we approach are C, equal to 0s0, 1s0, 000, 010, 0s0, 110, b00 and b10, where mi equal to 1 if machine I is processing parts, mi equal to 0 if machine I is under repair, b if machine 1 is blocked and s if machine 2 is starved. A state can be expressed by m1, m2 and 0, where the third digit is 0, implying a buffer's absence. Under the above-mentioned assumption, the operation of the line can be described as a continuous time Markovian chain. Its rate transition rate diagram is depicted in an adjacent figure and its corresponding transition matrix is Q. In the first estimation problem, 7 variables were used: lambda 1, lambda 2, mi1, mi2, ρ1, ρ2 and x2, which is the target variable. In the second estimation problem, an extra variable, x1, added in each case, corresponding to the throughput of the reliable line 1 of the system. That variable is supposed to boost the generalization power of the intelligent approach used. The final estimation models were tested in 1,000 new, unseen cases, 7 variables for first estimation problem and 8 variables for second estimation problem, that were produced with the same process into the range of the training dataset. The data sampling introduces a high degree of imbalance, making it difficult for the algorithms used to cope with the fitness cases. To deal with this problem, the mean values of 3 variables receive the values taken from Table 1 of the work of Eve Dallery and Stanley B. Gershwin, 1992, to approximate almost balanced lines with different failure and repair times. In this work, to approach the modeling problem of an unreliable two-machine production line with random processing times. Two computational intelligence methods were applied: multi-layer perceptrons and genetic programming. The final estimation models were developed and validated using two known validation methods: K-fold cross-validation, K equal to 10, and use test set equal to 1000 unknown cases. Finally, the statistical validation criteria used during these two validation processes were correlation coefficient, R, mean absolute error, MAE, root mean squared error, RMSE, relative absolute error, RAE, and root relative squared error, RRSE. The MLP model for the first estimation problem, resulting from a specific experimental process of testing various MLP architectures, presented in our work, is a three-layer network with one input layer with 6 nodes, one hidden layer with 8 nodes, one output layer with 1 node. The learning algorithm of this network was error backpropagation algorithm with learning rate at 0.2 and momentum at 0.3. Finally, the number of training epochs was 100,000 and the activation function of hidden layer was the logistic sigmoid. The performance of this model is quite satisfactory, as the correlation between the actual and estimated values is equal to 1, both during the training, with the 10-fold cross-validation, and testing process, using 1000 new cases. Also, the model shows that it can generalize as it presents a very low root relative squared error. For the second estimation problem, that resulting following exactly the same experimental process as we followed in the previous estimation model, is a corresponding MLP model with the only difference that has 7 inputs. In the hidden layer there are 15 nodes, and the training algorithm was fixed at the values 0.3 and 0.2 corresponding to learning rate and momentum. The performance of this model is just as satisfactory as the previous one, as we can see both in the performance table and in the correlation diagram. The GP model for the first estimation problem, described by this equation, as we can see in the next slide, shows equally satisfactory performance but relatively lower than the corresponding MLP model. Specifically, as we can see in the table, the correlation between actual and estimated values is lower than the correlation presented by the corresponding MLP model, and possibly the specific model does not generalize to the extent that the corresponding MLP model generalizes, as it presents a larger RRSE from the RRSE of the MLP model. Finally, for the second estimation problem, we have a corresponding GP model described by this equation. The specific GP model, like the corresponding model for the first estimation problem, shows quite satisfactory performance, but relatively lower than the corresponding MLP model, as we can see in the corresponding performance table. In conclusion, in this work, we have dealt with the problem of estimating throughput for a very short, two-stage, unvariable production line with one machine per stage serving at random times following the exponential distribution. A problem that almost directly affects global E and which, as we mentioned at the beginning, has been studied for many years, from 1960, and so far no corresponding model has been developed for large production lines. The machines are subject to failure and repair times that again follow the exponential distribution. The mean times of each distribution have formed a fitness case for training an artificial neural network and a genetic programming algorithm. Both algorithms have given satisfactory results with small networks and formulas. The ANN's approach is highly accurate with high generalization ability. The GP approach produces more comprehensible solutions in the form of a mathematical formula. The current research continues, toward modeling larger and more complex production lines using intelligent techniques. Thank you.